All right, here we go. We are in chapter 10. This is the second video. In this video, we are going to be looking at how you assign oxidation states. Another name for oxidation states is oxidation numbers. I'll kind of interchange them, so bear with me. Oxidation states, oxidation numbers. How do you assign them in a compound so that when you're looking at a reaction, you can determine what has gained and what has lost electrons? There are a few methods. There's two methods of these. There's one that is not as used, but it is helpful for some cases. And then there's another one that has a bunch of lists of rules and stuff. So when you're looking at oxidation state, okay, you're trying to assign how many valence electrons an atom has. Now remember when we were doing Lewis dot structures, the goal was to get everyone with a filled octet. And so you could count, okay, so here's an example. Here you can see water up here, the dot structure. We would say, hey, that oxygen has 2 lone pairs, 2 bonding pairs, it has 8 electrons around it. We would say, hey, look at that hydrogen. There's a bond between the hydrogen and oxygen that has 2 electrons. That hydrogen gets to count those 2 electrons to fulfill its duet as well. So we got to double count those electrons in some ways between the oxygen and the hydrogen. When you do oxidation state, you don't get to do that. You kind of have to just pick one thing to get them. So here are some of these rules, all right? So these are arbitrary numbers, okay? They're not really the charges, but sometimes they kind of look like it, and we'll kind of use the charges in some ways as well. Here are the rules to assign oxidation states in this bookkeeping method. All right, so if you have any lone pairs on an atom, they get to count for that atom. So if you look at the oxygen, it has 2 lone pairs, so it gets to count those electrons on that lone pair. Now, the bonding electrons, you don't get to double count this time. They will belong to the atom that's more electronegative. So in this case, you have the bond between oxygen and hydrogen. Oxygen's more electronegative. It gets to count those electrons for itself. Now, if you have like H2, okay, now one hydrogen or the other one wouldn't be more electronegative than the other, then they split it between the two. They each would get to count 1. So in this case, as far as assigning oxidation numbers go, the oxygen gets to count 8, all right, and the hydrogen has to count 0. Let's look, I think I have the next slide kind of working this through. And so then in order to actually then find the oxidation state, you have to do a comparison. How many valence electrons it kind of came in with as the free element by itself, and then you're going to be subtracting the number that we have just counted when we were looking at there and going through those rules. And then when you subtract those, that would be your oxidation state. So for the oxygen, it normally would come in with 6 valence electrons. We said that it gets to count the lone pairs, so that was 4, plus it gets to count both the electrons in the bonding pairs because oxygen is more electronegative than the hydrogen. So it gets to count 8 there. So when you subtract here, we'll get -2. So 6 minus 8 is -2. Each of these hydrogens are going to be the same, okay? They both are set up the same. They both only have 1 bond. So they both come in with 1, okay? It's valence electrons for one hydrogen would be just 1 electron. It doesn't get to count any, okay? There is a bond with 2 electrons between the hydrogen and oxygen, but oxygen was more electronegative and got to count it. So you can see it gets to count 0. So its oxidation state, subtract there 1 minus 0, and you get +1. One thing you want to note, water is neutral, and if you add up the oxidation states for all of the atoms involved, -2 plus 1 plus 1, you should get 0 because it's a neutral compound. All right, so those are the oxidation states. For that compound, I have another compound showing up here, NH2F. Let's kind of just go through this bookkeeping method again to figure out what is the oxidation state or oxidation number for the nitrogen, hydrogen, and fluorine. All right, so using those rules, first think of valence electrons. All right, so nitrogen comes in with 5. Let's see, nope, and then I went to 6. Let's go here, let's look. The nitrogen gets to count what? All right, it gets to count the 2 from the lone pair. Those count for it. And then it has a bond between the nitrogen and the hydrogen. It actually has 2 of those, right? Nitrogen's more electronegative, so it gets to count those electrons. The hydrogen doesn't get to count them. And so that would be a total of 6. Now there's also a bond between the nitrogen and fluorine. Those 2 electrons will go to the fluorine because fluorine's more electronegative. So nitrogen gets to count the 2 electrons between each of the nitrogen-hydrogen bonds and the 2 electrons in the lone pair, so a total of 6. 5 minus 6, we have -1 here. Fluorine, all right, let's go through that, comes in with 7 valence electrons. Okay, this is some stuff from before. Now we get to count the lone pairs. So there's 2, 4, 6, 3 lone pairs, so 6 electrons there, plus a bond between the fluorine and nitrogen. Fluorine's more electronegative, so it gets to count both of those electrons for a total of 8 electrons. Do some subtraction, and you have 7 minus 8, also -1 there for the fluorine on its oxidation state. Next, we have hydrogen. They're going to be the same here. Okay, they're both hydrogen with a bond to nitrogen. They both come in with 1 valence electron. They don't get to count the bond electrons at all because nitrogen's more electronegative, so they get to count 0. And you can see that the total adds up to +1. Again, this is a neutral compound. If you add up the oxidation states from the nitrogen, fluorine, and the 2 hydrogens, you end up with 0. That will be important. I think here is just a couple little, the textbook always wants to give you, here's the steps by what we do. Draw a dot diagram, then figure out total number of valence electrons it came in with, how many gets to count in the structure based on these counting rules, do a subtraction, and make sure that if it's a neutral, it added up to 0. If there was a charge on the molecule, the oxidation states will add up to that charge. All right, so that was the method of using the bookkeeping. Now here is the shortcut, and these are some rules. Now, these are rules that you should understand how they go. There's a couple things in here you should really just kind of have a good understanding of. And I think sometimes it's faster to use these rules, but sometimes it helps to do the bookkeeping method. All right, the first rule says that if you have something that is in its free state or it's uncombined, its oxidation state is 0. So this is true for things such as sulfur, which is S8. Even though there's 8 of them, it's just uncombined with any other element. So it's just a single element. So other diatomics would also be the same, like H2. Its oxidation state would be 0. Also, other things that are uncombined. So like if you have solid aluminum, oh, that was the example right there, and zinc. If they're solid, okay, they're not dissolved in solution, they're not an ionic compound, it's just solid aluminum, solid zinc. Oxidation state also 0. All right, now if you have an ion, and if it's a monoatomic ion, then whatever the charge of the ion is, that is the oxidation number. So example, if you have magnesium plus 2, its oxidation state or oxidation number is +2. If you have aluminum this time in solution, Al3 plus aqueous, okay, do you see a difference between aluminum solid, that's just solid metal, versus aluminum aqueous in solution? Okay, there you can tell by its state, and you can tell that this one has a charge here. So whatever the charge is for this ion, that would be its oxidation number. Let's just pick an anion for an example as well. Let's just pick Cl minus. All right, it's got a negative charge. Its oxidation state would be -1. All right, we have talked about this a little bit already, but the oxidation numbers in a neutral compound will add up to 0. This is a helpful rule because sometimes you'll know the oxidation state for one element but not the other ones, and then you can use this rule to kind of figure out what the other oxidation states are since you know they have to add up to 0. Next slide. Continuing on with some of these rules. If you have an alkali metal and it's in a compound, its oxidation state will always be +1. And if you have an alkaline earth metal, that's group 2A, its oxidation state will be +2. This is when it's in a compound. So remember, Na solid, okay, its oxidation state would be 0. But now if you have NaCl, the oxidation state on that sodium isn't going to be 0 now. Now it's with something, and we know that the oxidation numbers have to add up to 0 since this is neutral. The alkali metal will be +1, and then that means that the chlorine will be -1, which brings us to that next rule right here, looking at the halogens. Now fluorine, no exceptions here, will always be -1. Now the other halogens, chlorine, bromine, iodine, those will almost always also be -1. Now there are some exceptions, and one rule is if you have two halogens together, not very common, but if you have a fluorine-chlorine compound, the fluorine will win out and be -1. However, the chlorine could now have a positive charge. All right, and then the next rule, this is about hydrogen. For the most part, your hydrogen will be +1. Now, there are some examples of metal hydrides. So that's when you have a metal and hydrogen together. And in this case, especially if you have a group 1A or group 2A metal, they will win out and be +1. And then the hydrogen here is a -1. All right, so we'll see that a little bit. We also will have an example when you have oxygen. Okay, oxygen in a compound is usually -2. So here you go, you have oxygen gas. Now oxidation state there, it's just oxygen by itself, so its oxidation state is 0. But now you put oxygen in a compound, let's say H2O. Now the oxidation state for the oxygen is going to be -2. That looks like a 0. So the oxidation state or oxidation number, ON for oxidation number, for oxygen here is -2, and the hydrogen is +1. There's a couple examples here where oxygen isn't -2, but it actually ends up being -1. And these are in examples of peroxides. So hydrogen peroxide is an example here. Hydrogen peroxide is H2O2. So usually you say, hey, all the hydrogens are +1 and the oxygens are -2. Well, if you did that, that wouldn't add up to 0. You'd have +2 and a -4 if you add up the two hydrogens and the two oxygens. So that doesn't add up to 0. So something must not be right there. In this case, the hydrogen will end up still being +1. And the oxygen ends up being -1 in these peroxides. Also, if oxygen is with fluorine, you can't have two things that are minus. You have to have something with a plus. So fluorine would be the -1, and then the oxygen ends up being a +1. All right, I think those are all of the examples. Let's see how we use these. All right, we have just learned two different methods for assigning oxidation number. Oxidation number is what we will use to figure out what has gained or lost electrons in a reaction. So let's just do some practice at identifying oxidation numbers before we actually look at reactions. So the rules that you want to follow, either that bookkeeping method or the shortcut list of rules, either one of those works. Oftentimes I'll go to the shortcut list of rules first. So let's look at this first example. I think on this page I have 8 different examples for you to do. I'm going to just do a few of them and let you fill in the rest on your own. All right, CH3Br3. Now first off, you notice that this molecule has no charge, so when we add up the oxidation numbers, they're going to add up to 0. Okay, so we have that figured out. Now I like the circle and box method. The reason is I like to write out the oxidation number for just one bromine or one hydrogen, one carbon in the circle. Now there are 3 bromines here, so we're going to add those up to get the number in the box, and it's the numbers in the boxes that have to add up to 0. However, when you say, well, what's the oxidation number for bromine, you don't say what it is for 3 bromines, you just say 1. So you're going to say the numbers in the circle. All right, as far as the rules go, sometimes you have rules for everything and sometimes you don't. And since you know it has to equal 0, you just have to kind of use some math and some algebra to figure out, well, the thing that you don't know. In this case, okay, carbon, hydrogen, and bromine, we know the rule for bromine. Okay, the halogens will be -1 in most situations, so that would be going right here. So if I ask what's the oxidation state of the bromine in this molecule, you would say it's -1. Now there's 3 bromines, okay, so the total will be -3, even though you just report for one of the bromines. Now the hydrogen, for the most part, okay, there was a couple exceptions, but will be +1. There's only one of them, so if there's only one hydrogen, the number in the circle and in the box will be the same. All right, and now the carbon, there was not a specific rule for carbon, and carbon's oxidation state can vary based on what it's with. So we have to kind of use these numbers, and since we know it adds up to 0, we can figure out that +2 + 1 - 3 equals 0. So this has to be +2. So +2 + 1 is +3 - 3 gives us 0. Since there's only one carbon, the number in the circle and the box is the same. And now we've found the oxidation numbers for the carbon is +2, the hydrogen is +1, and the bromine -1, each of them. All right, next example here we have ClO3 -1. So here's a case where you have an ion, okay, a polyatomic ion in this case, and so our total number, or the total oxidation numbers have to add up to the charge of the ion. All right, now we do the same process again. Now usually chlorine, okay, is a halogen, it's going to be -1. However, oxygen, the rule for that will hold out first. All right, and we know that oxygen's all going to be -2. And there's 3 of them, so that leads you to -6. So we have to say what -6 equals -1, and you would say +5. So the oxidation state, since there's only one chlorine, for the oxidation state for chlorine, or the oxidation number, same thing there, is +5, and each of the oxygens has an oxidation number or oxidation state at -2. One more example, manganese, I'm not even going to say the whole name, you can probably get it from the name here, but let's find its oxidation state. Manganese is a transition metal, it could have varying charges. We know overall this is a neutral compound, so the oxidation numbers will add up to 0. Manganese we don't know, okay, there's not a hard rule for those, but we do know the rule for oxygen. I think we've had oxygen in the previous one, it's going to be -2. Now there's 2 oxygens in here, so if you add up the total contribution of oxygen to the oxidation numbers, that would be -4. And so in this other box here we have to say what -4 is 0, that should be +4. And since there's only one manganese here, this has got to be a +4 as well. So the oxidation state of manganese is +4, oxidation state of oxygen is -2. All right, based on this, we're going to go in the next little video, we're going to start putting this together with reactions and figure out what's being oxidized and what's being reduced. All right, one last example now that we're going to go through. Now that we have used the circle and the square methods, can you do this and set this problem up? Oxidation number of the chromium in Na2Cr2O7. Let's work this one out together. I'm going to put the circle in the boxes here. This is neutral, so it will add up to 0. And let's go through our rules. Sodium is an alkali metal, it's in a compound, so we know it's going to be a +1. And the oxygen, okay, is in a compound, so we know it's going to be a -2. It's not in a peroxide and it's not with a fluorine, so it will be a +2. Let's do our math here. All right, we have each sodium's +1, but there's 2 of them, so this is +2. And we have oxygen, and there's 7 of them at -2, so this is -14. +2 plus what? -14 gives us 0. This has to be +12, fits in that blank, right? Now, what goes in the circle? There's 2 chromiums here, so we would say each chromium then has a +6 charge. So correct answer here, +6. All right, and then this one, here you have oxygen. Students want to so quickly say, hey, oxygen's -2. Is that true in this case? We have oxygen by itself, uncombined in its natural state. Its oxidation state will be 0 here.